Right. Well, welcome back, folks. Glad to see that more of you were able to draw those pictures and be able to interpret what you see on a velocity time graph here to the actual motion itself of an object as it moves in one dimension. Okay, so make sure you practice. If you have any questions on this, come by and you see me and get your questions answered. Okay, but we do have to continue on, and I want to continue on by using this the graph here, these graphs here, in order to obtain equations, formulas that we can use to be able to predict how the object moves. Okay, so let's imagine what we have here. Okay, so we can use this graph here, for example. Okay, for example, and I asked you to do this here. If we wanted to find out then how fast the blue object was moving, how fast the blue object was moving, let's say at 5 seconds or 6 seconds. Assuming that this object continues on this trend here where it's moving at a constant acceleration, we can extrapolate the graph. That means that we can take a ruler and extend the y-axis, extend the x-axis, and then find the intersection between the blue line here and 5 seconds, trace it over to the y-axis to find out how fast the object is moving at 5 seconds. Okay? Because obviously within this graph right now, within the graph, we don't have that information. We have to do what's called extrapolate. Okay. And so when we extrapolate from a graph, what we're doing is we are extending the graph beyond the data set that is given here. So this data set here only gives us from 10 seconds to 10 seconds in terms of the time interval and 10 meters per second in terms of the velocity. Okay, so you can extrapolate for the blue graph here to see what happens at 5 seconds. Okay? So with that said, then you can also extend the time here. Let's say the objects continue to move. You can extend the time here to extrapolate then what may happen for the blue object or the red object as it moves beyond 10 seconds. So extrapolation is taking information from a graph and trying to extend it, see what happens. Okay. Now, with that said, then let's say we got these graphs here and we want to obtain data points that are, and from the graph, then obtain data points that were not originally used or originally not obtained to generate the graph itself. Okay, so what we do then is, in that case, then we can interpolate. Okay? Interpolation means then that we take the information that is given from the graph here, and to conclude some things about the object's motion that was not originally was not originally seen in the original data set. So most of these graphs are obtained from taking some recordings, getting a data set, and then graphing those points on this graph here. And so what we can do then is we can find out information about, let's say, how this object moves within this time interval and within this velocity here, if we did not originally record it. If we didn't originally record it before, but we did want to find out how this object moves at some other time within this data set here, we can do what's called interpolation. That means go within the graph itself to get that information. Okay? So we can use this graph here to obtain more information, make predictive. These graphs here are also predictive, which means that we can use these graphs to predict what would happen outside of the set of data that we originally collected. So we originally collected some data, we originally made some observations, and then we made this graph out of it. From this graph, that we can use it to predict what will happen for a set of data that is outside the data set, and also a set of data inside. So when we extrapolate, we're going outside the graph. Okay, so we're going outside the graph when we extrapolate, and when we interpolate, then we're staying inside the graph to obtain the information. Okay, so graphing then is a very important, powerful tool that we can use not only to kind of get an idea of how the object moves. That was the whole idea behind the exercises last week where we actually drew out the pictures, but we can now use graphs as a predictive tool, and that is what we want to do moving forward. Okay, so we can use the graph as a predictive tool in order to decide then what happens outside here and within the graph itself. Okay, all right. But graphs are still fairly cumbersome, folks. You have to be able to use it, you have to be able to generate it. Okay? And so the whole idea then is, can we simplify the information? Can we simplify the information even more obtained from the graph and use that as a predictive tool? And the answer is yes. And we did that, okay? And that is, we can come up with formulas, and we can derive a formula from the graph. Then we can use the formula instead of the graph in order to make predictions about what will happen, okay? And we saw then, when we looked at this graph, or we saw then that these slopes here, the slopes of the lines, okay? The slopes of the lines on a velocity time graph, okay, so the slopes of the line corresponds to the acceleration, okay? And we saw that that was happening because the slope of the line then measures then, remember, the rise over the run, which is the change in y over the change in x. From this graph here then, from the graph then, the change in y is going to be the change in velocity, okay? And the change in time is going to be then, change in x is going to be the change in time, which when we write that down then is going to be delta v over delta t, which when we simplify then is going to be delta v over t, which represents a time interval. And what is the change in velocity over change in time but what we refer to as acceleration? So we obtained this information here. We were able to get that graph, that formula from this particular graph of a velocity, from this particular graph. So the slope of the line, of any line on a velocity time graph then will give us the acceleration. So the slope from a velocity time graph, gives us the acceleration. And so that means then, if we take a look at this and let's expand this, okay, the acceleration then takes into account a change in velocity, remember, is v final minus v initial, all over the time interval there, okay? So there is an equation now that we can use to extrapolate outside and find then, let's say, velocities, final velocities that are outside of the slope here, okay? And we did that, and I asked, I asked you to consider that earlier on. So let's go ahead then and let's remind ourselves that earlier on we had done this problem here where we had plotted out the motion of the object, okay, motion of the object on this blue line here, okay? And so I told you then, we saw then that the acceleration, since the slope is constant, okay, the acceleration is constant. The acceleration then is 5 meters per second squared. Okay, so we saw that the acceleration at every one of the time intervals here is constant. We saw that the slope is constant, okay? We saw then that the initial velocity then is 0. Okay, we saw the initial velocity is 0, means it's at rest, 0 meters per second. Or we can look at each time interval here and try to get that as well, okay? And so in this particular problem here, so we were able to calculate for the accelerations here with v final and v initial within each of these time intervals, and that's how we were able to obtain these accelerations here. But what I asked you to do, what I asked you to consider then, is if you know this acceleration, and if you know this velocity, and if you were asked about the time interval here of 5 seconds, okay, that means then the object we're going to measure from 0 seconds all the way to 3 seconds. I'm sorry, 3 seconds. Let me go and erase this. I asked about 3 seconds, not 5. Okay. Okay. At 3 seconds, at a 3 second time interval. So the time interval here is from 0 to 3 seconds. So a 3 second time interval. Could we find the velocity at that point, which we would consider then v final? Could we do that? Well, absolutely, we can do that. Okay, so let's go ahead then and let's take a look at how we would do that. So all this information here we obtained from the graph. So all that information we obtained from the graph. Okay, so let's go ahead then and let's consider this particular problem here. Okay, now let's calculate for it. Okay, whoops, sorry. Oh boy, I thought I had a graph here. Sorry. All right. So let's go ahead and let's consider what we have here. Now I'll just work it out for you underneath here. Okay. All right. So we know then that the acceleration, let's work it out up here. The acceleration is v final minus v initial all over time. Okay. Given this information here, if we're trying to solve for v final, we can rearrange this equation here. Okay. And we'll talk about this much more later. Okay. V final here is going to be equal to v initial plus a times t. This is something that we should be able to do, and this is the first step in the first equation that we're going to use to solve for different components of this motion here. This is the essence of kinematics. Okay? But in order to get to this point here, folks, we have to be able to use this equation here first and understand what it means when it comes to solving for acceleration. And that's what I want to work on right now first, and then we'll get back to this problem here that I asked you, this problem here that I asked you, okay, in just a moment, okay? All right, so let's go ahead, let's solve for acceleration. Now, I think that would be the easier of the two calculations. Let's take a look at this problem here, okay? And let's work this one out together, okay? All right, so read the problem here, okay, and they want you to find then the acceleration. They want you to find the acceleration of this particular object here, which is a baseball player at point A, point B, and point C. Before we do that, what I'd like you to do is on your paper, I want you to plot. I want you to show me how this person is moving. This person's moving in a straight line as he's going to catch the ball. Okay, so go ahead and draw that picture really quickly. And I want to just more practice interpreting the graph, and then I want to use this graph to work this out with you. Okay, so let's go ahead, take about a couple of minutes, draw out the picture. Okay, let's draw this picture here. Let's see how this object, let's see how this baseball player is moving. Okay, so we're saying then that the baseball player is moving in a straight direction. Okay, we're looking at then, I'll just draw it right here. Okay, at time is equal to 0, and so we'll call this t is equal to 0. Okay, he starts his motion. Okay, so he's moving in a straight line now. Remember, we're talking about a straight line path here, so he's not turning. So this is a straight line path. So there's your straight line. Okay. All right, so he starts out, okay, and at t is equal to 0 here, okay, so here's our object, okay, mass m. At t is equal to 0, we see then that he's not moving. The velocity is 0. This is a velocity time graph now, and I'm sorry, I got cut off here, but velocity time graph, at v is equal to 0 seconds, he is not moving, 0 meters per second. Then he starts to move, okay, then he starts to move. And as you notice here, as he starts to move, and let's call this here at t is equal to 2 seconds, okay, at t is equal to 2 seconds, okay, we see then if we trace it up, he's moving at a speed of, and we'll call this v2, v at 2 seconds, 4 meters per second. Okay, all right, so let's go ahead and let's continue, and I'm going to plot this out a little bit further than that. Okay, so let's go ahead and let me draw the picture. Let's plot this out a little bit further than that, give myself more room. Okay, and then let's go ahead then and let's take a look at 3 seconds. Okay, okay, at t is equal to 3 seconds, let me go and write this down here. Then you see then at t is equal to 3 seconds, is velocity at this point then is still 4 meters per second. Okay, all right. And so with that said, then let's take this out to the last one. T is equal to, t is equal to 4 seconds. Okay. Okay. Let's take that out to t is equal to 4 seconds. And therefore at v4, we have then speed is 2 meters per second. Okay. So we have 3 different time intervals that we're going to look at here. Okay. So what I'd like us to do then, what the question is asking you to do is, what's the acceleration here? And we'll call this acceleration 1. Okay. What's that acceleration? Okay. What's the acceleration here at point 2? What's the acceleration here at interval 3? So we want to find the accelerations at each one of these here. Be able to draw out this picture. So he's still moving in a straight line, folks. Moving in a straight line. The question then is, does he? Do we know where he's at? Does he turn around at this point, or does he turn around and come back? Okay, and that's a question you need to be able to answer. If you're not quite sure how to answer that question, make sure you come by and see me. But remember, he doesn't turn back. He's moving in a straight line. So if you're not clear on why that is, make sure you come see me. Okay. All right. So they want us to solve for that. Let's go ahead and work this one out together. Okay. Okay. So acceleration then, so we're going to be using the equation here. Okay, acceleration, since this is slope, and so instead of using the slope, let's use the equation here then of delta v over time interval. Okay, let's take a look at the first one. Okay, let's take a look at the first one. Okay, so at a is equal to 1. Okay, and well, let me go ahead and do this. Let's go ahead and let me save this here for you. Clear this out. Let me get a new slide here for you. Okay, so we have more room to work with. Okay. So hopefully you have that written down in front of you. Okay, let's go ahead and solve for acceleration in the first time interval. Okay. In that first time interval, we saw then that, and again, I'll write up here the equation. Acceleration is going to be delta V is equal to time interval, which is equal to V final minus V initial all over the time interval itself. Okay, so for the first time interval, remember here, we're looking at time 0 to time 2 seconds. Okay, all right, so the acceleration, let's go ahead and calculate for the acceleration. Let me go ahead and give myself some more room here. So this is the first time interval here, t0 to t 2 seconds. Okay, the acceleration then is going to be equal to delta V over time interval, which is V final minus V initial all over the time interval here, T final minus T initial. We have then, and I'll write this in here for you. Okay. We have then V final, make sure you keep this in mind, was 4 seconds. Okay. V initial was 0 seconds. Okay. And the time interval then is going to be a 2 second time interval. Okay, so plugging what we have in here. So this is the first time interval. Okay, plugging in what we have here. V final then is going to be 4 meters per second. V initial then is going to be 0 meters per second, all over time interval of 2 seconds. And so therefore the acceleration then, we plug that in, it's going to be a positive 2.0 meters per second squared. So that's the acceleration for the first time interval. Let's go ahead and let's take a look at the second time interval. Okay, so the second time interval was t 2 seconds, from 2 seconds to t to 3 seconds. So we're looking at this time interval now. Okay, and let's go ahead then and using this same equation then, and I'm just going to shorten it a little bit here, just include this. It's going to be V final minus V initial all over t. Let's identify what we're given here. Within this time interval here then, V final was 4 seconds. Oops, sorry. V final, let me rewrite this here. V final was 4 seconds. V initial was also 4 seconds. And the time interval here was a 1 second time interval. We'll go and write that in. Okay. And so let's go ahead and plug in what we have here. V final was 4 seconds, 4 meters per second, sorry, 4 meters per second. So we have then 4 meters per second. We have for the V initial was 4 meters per second, and over time interval of 1 second. And if you notice here, then the acceleration here is going to be 0 meters per second in this second time interval. Okay. All right, let's take a look at the third time interval here. So I'm going to have to squeeze it down here. The third time interval then was between 4 seconds, between 2 and I'm sorry, 3 and 4 seconds. Sorry, 3 seconds, and t is equal to 4 seconds. Okay, let's go ahead and write that in. The acceleration then is going to be v final minus v initial all over time. So I have to squeeze it in down here. I can't write this in for you, but you write this out yourself. Okay? So v final here is going to be 2 meters per second, which is the speed at 4 seconds. 2 meters per second minus the initial velocity at t equal to 2 seconds, which is 2 seconds, which is 4 meters per second, all over time interval of 2 seconds here. Okay? Which gives us here a negative 2.0 meters per second squared. Not sorry, this is second squared as well. Okay. All right. So what can so that those are the accelerations there. So make sure you're able to do the calculations first and foremost. Okay. But let's quickly interpret what we have. Let's quickly interpret what we have. Right? And there's no graphs here. Okay. So we're just writing this out. So does this make sense? Okay, and what's happening? Well, first of all, what's happening here is that the baseball player is speeding up. Oh, sorry. Issues with the board again. Okay, speeding up. So the object here is speeding up. Okay, and how do we know that? Well, first of all, from the graph, we saw then that there was a positive slope. Okay, that we see. But further, what we notice here then is that we have then the acceleration is positive, and the velocities here are also positive. And so when we have the same sign here, okay, same sign, okay, we know then that the object is speeding up. Okay, let's continue on here. Here we see then that the baseball player is maintaining, and let me just take a few more minutes here, folks, maintaining constant speed. Okay, and how do we know that the object is maintaining a constant speed? Well, slope is equal to 0. Okay, and when that's the case, then acceleration will be equal to 0, and that's what we have here. And what we notice then is v final and v initial are the same, and that's exactly what we have here. So when the velocity does not change, when v final, v initial is the same, the acceleration is 0, which means then that it's maintaining constant speed. Finally, if we take a look at the last one here, we see then that the object is slowing down. Okay, and so how do we know it's slowing down? Negative slope. You have a negative slope, and also the signs are opposite. We have acceleration here, which is negative. Okay, velocity, which is still positive. Velocity is positive, and so therefore they have opposite signs. And I'm sorry, didn't mean to squeeze it in there, but you get the idea. So opposite signs here, positive value here, negative value for acceleration. Opposite signs mean the object is slowing down. Okay, right. So this is what we need to be able to do. We need to be able to calculate very simply the acceleration. So we want to start focusing on calculating our values in order to make predictions rather than relying on the graph. Again, the graphs are great, but they're fairly cumbersome. So we want to make sure we're able to use these formulas here. And tomorrow what we're going to do is we're going to go ahead then and solve for some other factors that you'll need, other variables that you'll need to be able to calculate for as well. Okay. All right, so very good, folks. Come by and see me if you have any questions about this, but I think this is pretty straightforward. I'll be available today after school from 1:30 to 2:30. Come on by and get your questions answered, okay? If not, I will see you folks tomorrow. Have a good day.